Welcome to a lesson with Dr. Powell. Let's take a look at an example of solving a system of equations. Okay, you'll notice there are variables x, y, z, and w right here. And, um, and notice how we've kind of written this, right? So like -1 times x plus 1 plus y plus 1 times z plus 0 times w is supposed to be equal to 1. Now, really what we're doing when we write out this system of equations is the following. We're thinking of negative. In fact, if we just kind of clear out these guys right here, what do you notice? You notice a matrix, right? Of coefficients. And it's a matrix map. What's its input? Its input is or its domain is R4. Notice there was an X, Y, Z, W. Those are like that's like an input into the function, X, Y, Z, and W. This is like right over here is like the so equal, that was an equal sign. This over here would be like the output of the function. -1 or 1, -1, -1. And what we're doing quite literally is we're taking x and multiplying x to the whole first column times x, second column times y, third column times z, and fourth column times w, adding them together and see if we get this. That's the same thing as having a system of three equations and four unknowns, because we have -1 times, because this is a scalar and we can multiply it through to each component of this vector. And so it's like -1x and then plus 1y plus 1z plus 0w is equal to 1. So we end up actually getting the idea that we're plugging this into this matrix function. So what we could do is we could say, okay, we plug it in. So by writing it on this side, x, y, z, w, and then that's going to be equal to this. Maybe we'll rewrite it over here so it'll give us a little bit more space. All right. So when we do this matrix multiplication right here, or rather input this into here, we get this. So kind of what we're doing is we're trying to find out all input vectors that gives us this output. If we label this matrix function as an f, really what we're doing is we're finding the pre-image of this codomain element. So what's everything that maps to here? It is possible that sometimes nothing will map to it. So the pre-image would be empty. And since sometimes it also has something in it that maps to it. And maybe that's what we're looking for. So the pre-image of just a single element is called a fiber. So we're looking for the fiber over this codomain element right here, which lives in the codomain of this matrix function. And we'll call it, so it's 1, -1, -1. It's a 3-tuple. We're finding the pre-image of it. Okay, so now this matrix function is an additive function, which means every single fiber, if it's non-empty, is simply a shift of the zero fiber. So this will be equal to some vector, just one vector, added to all of the fiber over zero, which is called the kernel. In other words, the preimage of this is a single vector shifted by a whole subspace of the domain, which is because the kernel, or the preimage of zero, is a subspace itself, a vector space of the domain. Or you can think of it as this whole subspace, but just shifted over by V. Sometimes this subspace, well, think about what it could be. It could be a straight line. It could be a point. It could be a plane. But it goes through the origin. And then what this is this just a vector that we shift it by. So perhaps we have a plane going through the origin, and that's the fiber over zero. But then if we shift it by a vector V over here, then this plane would not go through 0, 0, but it would be a whole plane. And so really what we're trying to show is that all the solutions to a system of equations actually make up a shift of a vector space. Now, a vector spaces could be points, lines, planes, at least for us if we're working in R3, or all of space, or some higher dimension analog of these things. And so it's just going to be a shift of a vector space. So fibers themselves aren't vector spaces, but they are shifts of vector spaces. Okay. So understanding that is important for what we're about to do in solving the system of equations. We're going to do two things. The first thing that we're going to do is we're going to find the vector v to shift by. And then the next thing we'll do is we find the kernel. To find the vector v, to make it simpler, we're going to first find the reduced row echelon form, row echelon form, RREF, of this matrix. So what is that? That's like doing all the row operations that we possibly can to this matrix. And I guess we're calling it F, so we could just use F for the matrix as a matrix function. Then to find the kernel, what we're actually going to do then at that point is we're going to do some column operations. And we'll talk about how we can do column operations to find this kernel. So we need both parts. The row operations will help us find the vector to shift by. The column operations will help us find the kernel. Okay, so pretty much in the end, what we're doing is we're finding the Smith normal form of this matrix in order to solve this system of equations, and which is the same as finding all the elements in this fiber. The row operations give us this part, the column operations will help us with that part. But first, we have to only do the row operations for here. So that's what we're starting. This is kind of the schematic, and we'll keep it in our minds as we go. All right. So first off, let's proceed here. Let's see. All right. Okay, let's keep that in mind and just go from here. All right. So we need to get a 1 in position up here. And in my mind, I'm thinking, we could multiply this by a negative, but it seems simpler to me to just swap rows. I'll just put this up here because as I airdrop this over to other things, the zeros will be nice. So I'll just do that. So I'll just write a 1, 0, 0, -2. And actually, as I do this, though, I think of an augmented matrix. Because realize what's happening here is we're doing an isomorphism on the output of this matrix function, so in the codomain. This guy lives in the codomain right now. So if we do something to the codomain, we're actually doing something to all these guys and to this guy at the same time. So because this should live in the span of these guys if we're successful, and it lives in the codomain. So if we do one thing to all this, we'll do it the same thing over here. Okay. So, and the nice thing about doing an isomorphism is it preserves linear combinations. And x, y, z, and w are actually just scalars for a linear combination. And so if it preserves linear combinations, if this is a linear combination of these, the result after applying row operations to this, which is an isomorphism, should preserve the same linear combination, x, y, z, and w, to equal whatever we get over here. So actually, the scalars that we need, x, y, z, and w, can actually easily be seen by simply just changing the linear combination question to a simpler front, which is exactly what the reduced row echelon form does. And we're working, which row operations, remember, are things we do to the codomain. So after the actual function. So if we swap this row with this one, remember this also swaps as well. So this whole guy right here is gonna, it's gonna change places with this guy up here. Okay, so we end up getting that, and then on the bottom, then we have a -1, 1, 1, 0, 1. And in the middle, that stays the same. 1, -1, -1, 0, -1. Okay, now we airdrop. Going down here. So that would, so now we airdrop going down here and here, because we want to make zeros down here. This will become a pivot. So as we do so, let's see, we take this whole row, multiply it by -1, and drop it on this guy right here in the middle. So that would give us 1, 0, 0, -2, -1. That would give us a 0 here. And of course, when we airdrop down there, it's going to be a 0. I'll put a -1 to remind me I'm multiplying by -1 for that guy. And this guy, it's just times +1 to go down. So that'll be a 0 here. 0 times anything, that is just -1 still. That's just -1. See how that was nice, putting those zeros there. Then here, this will be -1 times -2, which is +2. Added down would just be a 2. Then a -1 times a -1 is a +1. Plus a -1 would be a 0. Okay. Then I airdrop down here. So 1 and a -1 is a 0. I already have that. And then that doesn't change anything. And then here I have -2 times a 1, which should be a -2, so added down. And then here I have a -1 times a 1, which is -1, plus 1 is just a 0. Okay. So I end up getting this right here. Next, notice that these two rows are the exact same except for a negative. So this should be pretty simple. In fact, let's just multiply this one right here by -1. So just that's what I'm doing. So I see, and it looks the same. I airdrop, just multiplying by -1. And then these guys will just go away. All right, those will just be zeros. Now notice I have two pivots, one right here and one right here, and all the rows, so that every single row either has a pivot or it's zeros, which means this is actually reduced row echelon form. It's as far as I can go with row operations. I'll put a line right here to remind myself where the equal sign was in the equations. That this is the codomain element that we're trying to find linear combination of these guys to equal it. So let's just look at these and see if we can come up with a linear combination of these guys to equal this. This should be an easier situation, especially since we have these pivots going on right here. Okay. In fact, we can just solve the system by hand from this point, if we will. So let's remember what this is. This is like the scalars. So the linear combinations were preserved by the linear transformation maps. So we still have x times this column, y times this column, z times that column, w times that column that we're trying to equal that column. So we can kind of just write that out. So x times this column is just x0, y times that column is 0y, and w times that column is 0, or z, I guess it was a z, right? 0z, and this is -2w, -2w. And we want this to be equal to -1, and we want this to be equal to 0. There may be more than one thing that actually works. So all we have to do is just find one thing that works, and we'll be set. In fact, the simplest thing to do is just, make as many things 0 as possible. Since there's a 0 on this side, may as well just make these guys zeros. Okay, so those guys are zeros. These scalars, which would force x to be a scalar of -1. That would actually work. So we have our v. Guess what our v is? It's just, well, we just said it. X is -1, y is 0, z is 0, and w is 0. All right, now it's time to find the kernel. So we found our v. And what we did reduce row echelon form to help us find this vector v, which is going to be the shift of the kernel. Now we got to find the kernel. Okay, so let's see what we can do for that. Oh, right. So proceeding, we go ahead and we work from, and what we're going to do is we're actually going to work right from the point that we have for the reduced row echelon form. So let's just make these zeros right here. Okay, so those are zeros, and let's work from this point. Okay, so what we're going to do, okay, so what we're going to do now is the kernel is solving the system where we have zeros, right, on this side. So we can kind of just kind of ignore what's over there. Like, you know, what's going to make this 0? Now, since linear transformations always send 0 to, send 0 to 0, and kind of what we want to do in particular. So let's just kind of get a picture of what's happening. We have so we have our row operation, we have our f, and the column operations, what it's going to do, if you take the kernel of the Smith normal form, so you find the Smith normal form, you find the kernel or the fiber over 0 for it. So it's the kernel of the Smith normal form, and you pipe it through the columns, the column operations, you end up getting the kernel of f. So everything that f would take to 0. You just have to pipe in the kernel of the Smith normal form into the columns, and then you get f. One way of doing that is as follows. Realize that the columns coming in, okay, the column operations map, it's an isomorphism in the domain. The domain is our 4 right here of this matrix. So it's going to be a 4 by 4 matrix. It's going to have, okay, so because I have 4 columns here, and this is going to be a 4 by 4. All right. Now, whatever operations, column operations that I do to change the matrix, I'm going to use to change this, because the kernel of the whole Smith normal form is actually some of these columns. We have to just have, but we'll actually see which columns they will be as we go forward here. In fact, the columns that we get zeros in over here will actually be the columns over the zeros over here will correspond to the columns over here that on this side that will actually be the kernel of f, because we're going to be doing the column operations here, but we're going to apply them over here. And we end up getting as we apply the column operations over here, we end up getting a matrix that represents, we end up getting a matrix over here which actually comes before this guy. Because remember, as we do column operations, we have a map that comes before this guy and a one that comes before this guy. But the nice thing about this is the identity map. This is the identity function that just sends things to themselves. So if we get a function that happens before it, it's as if it happened after it too. So we can think of it in either way if we want. But we get this map over here, and actually the range of this map, right, of what we get over here is going to be just seen in the columns that we obtain on this side. Just doing the column operations, the identity matrix before actually gives us a map after the identity as well. And the columns that we see are actually the range of the column, column operations. And we can pick out which of these guys will actually be the kernel or span the kernel of f. By which ones we, by just examining which columns over here are zeros. So we proceed. Okay, so in doing column operations, all right, we can basically, they're just airdropping. Like this comes over here, airdrops, this comes over here, but we have to do it on this side. So let's think about what happens. like we do an airdrop, this guy all the way over to this -2. So we multiply this column by 2 and add it to that one. Over here, what would happen? Well, we'd do the same, well, we do the same basic thing. Okay, on this side. So this becomes a 2, while this one's cleared out. Okay, now, next we go down here and we take this and we clear out these. So when we clear out, that's like -1 times this guy, and that guy cancels out. That guy cancels out. So -1 times this guy and add it over. That's like -1 times this guy added over. So over here, it actually becomes, there's things that change and it looks less like the identity. Here, so 1 times -1 multiplied over or added over would be -1 here. And then over here, let's see, we have 2 times this and added over. So 2 times this and added over. So that would be a 2. All right. So in the end, we get 0, 0. So these two columns, all right, mean that actually so this is E3 and E4 in the combined total map, because this is the Smith-Normal form representing this whole map right here. And obviously it looks like E3 and E4 actually are the kernel. That's what goes to 0 under this map. So, but if we run them through, so take E3 and E4 and run them through the column map, this is the column map right here. E3 and E4, we run them in, and look what happens. They end up coming here and here. So that actually, these two vectors actually span the kernel. So we actually get that the fiber over this element is this vector plus the span of these two guys, 0, -1, 1, 0 as a vector, comma, 2, 2, 0, 1. And that concludes, okay, so and that concludes solving our system. We just found everything in here. In fact, we can even check this. If we plug -1 in, well, right, look at these scalars right here. If we put them in right here, yeah, that equals 1. If we put this in, let's see, -1, yep. Yeah, so that definitely is a solution. And then if you come here, if we add any one of these guys to it, to this, we should still have a solution. For instance, if we added on like this guy plus this guy, we would have -1, -1, 1, 0. Let's see what happens here. So -1 would be a +1, and then we'd have -1 would be, so -1 would be 0, and then we add 1, we get a 1. Notice, and we can try it out. We have successfully found all the solutions to this system of equations. Thanks for watching.